Recall that when calculating sample means, we were warned that outliers can have a big effect. Because least squares lines are built on means, you might think that outliers would have a big effect on regression line, and you would be correct. Outliers in regression are observations that fall far from the cloud of points. These points are especially important because they can have a strong influence on the least squares line. Here's example 4. There are 3 plots below along the least squares line and residual plots. For each scatter plot and residual plot, identify any obvious outliers and note how they influence the least squares line. Okay, let's take a look at the pair associated with number 1. So here's our least squares line here, and then here's our residual plot down below. So we can see that we do seem to have an outlier here. And if we look at our residual plot, it seems like we might have a bandwidth here, but still an outlier. But the bandwidth is kind of a little slanted. So let's write that down. So it looks like the residual plot is a little slanted. So it seems like the outlier has some influence, but not a lot. Okay, number 2. We have an outlier here that's far away from the cluster. And in our residual plot, we see the cluster here as well as the outlier over here. I don't know. It doesn't seem, since it kind of falls close to the regression line, it doesn't seem to make much of an impact on the regression line. So outlier, not much of an impact. Okay, and then here's the last one. We have an outlier up here. And down here for our residual plot, we can see that the bandwidth is kind of slanted again. So here, slanting downwards again. So the outlier has some influence. Okay, so these were our observations. Let's see how our answers compare with the actual answers. So for part 1, there is one outlier far from the other points, though it only appears to slightly influence the line. So we got that one right. For part 2, there is one outlier on the right, though it is quite close to the least squares line, which suggests that it wasn't very influential. So we got that one right too. And then part 3, there is one point far away from the cloud, and this outlier appears to pull the least squares line up on the right. So examine how the line around the primary cloud does not appear to fit very well. Okay, got that one too. Here's example 5. Here are an additional 3 plots below, along with the least squares line and residual plots. For each scatter plot and residual plot pair, identify any obvious outliers and note how they influence the least squares line. Okay, so just think in your mind. Got some issues here on the right hand side. We've got an outlier up here for number 2, and then we've got an outlier that's on the left hand side of our scatter plot here. So let's see how these influence. So for number 4 here, there is a primary cloud, and then there is a small secondary cloud of 4 outliers. The secondary cloud appears to be influencing the line somewhat strongly. See how it's kind of heading downwards on our residual plot? Making the least squares line fit poorly almost everywhere. There might be an interesting explanation for the dual clouds, which is something that could be investigated. Part 5. There's no obvious trend in the main cloud of points, and the outlier on the right appears to largely control the slope of the least squares line. So without the outlier, we wouldn't know if this cluster was increasing, decreasing. We wouldn't really have a good least squares line. For part 6, there is one outlier far from the cloud. However, it falls quite close to the least squares line and does not appear to be very influential. So points that fall horizontally away from the center of the cloud tend to pull harder on the line, so we call them points with high leverage. We've got this little quote down here, "Give me a place to stand, and with a lever I will move the whole world." Archimedes. Okay, so again, points that fall horizontally away from the center of the cloud tend to pull harder on the line. So we call these points with high leverage. If one of these high leverage points does appear to actually invoke its influence on the slope of the line, then we call it an influential point. Usually we can say a point is influential if we had fitted the line without it. So if we had fitted the line without it, the influential point would have been unusually far from the least squares line. So if you notice a point that's far away, you can try plotting your line without that point and see how it compares with plotting the line with that point. And if it's a drastic change, that's an influential point. Imagine there are 100 ordered pairs in the data set, with each of the 4 dots in the lower right representing 25 individuals. Notice that a linear model is a perfect fit to the data. So all 4 points line up exactly. We have an R, a correlation coefficient of 1, so it's a perfect fit. Now imagine a 101st point placed at the point 0, 20, so way up here. Notice that one single point changes the correlation from a perfect 1 to a negative 0.46. It would completely change the analysis of the data. It is tempting to remove outliers. Don't do this without a very good reason, such as an obvious typo. So if you were recording data and you accidentally wrote down the wrong number, then you could remove that. Models that ignore exceptional and interesting cases often perform poorly. For instance, if a financial firm ignored the largest market swings, or the outliers, they would go bankrupt by making poorly thought out investments. So in most cases, we will do an analysis with and without the outlier and just see if it makes a difference.